So recall that last lecture we talked about decomposition algorithm for mixed integer nonlinear programming, right? The high level idea is that let's assume if you don't know how to solve MNLP problem, but the continuous relaxation is convex, we kind of decompose the MNLP by MNLP and NLP problems, right? Then you can solve an MNLP and an NLP iteratively, and then you will converge at the optimal solution of the convex MNLP. That's a high-level idea. And in the next few lectures, we will talk about a couple of decomposition algorithms for a problem with a very special structure. In other words, those problems have so-called a decomposable structure. In the first lecture, we will talk about Bender's decomposition. Just a little bit history of Bender's decomposition. It's proposed by someone whose name is Bender's. So when you write Bender's decomposition, remember that Bender's is a name. Don't write Bender prime S in your paper, right? Just write Bender's. So in his PhD thesis, he proposed the paper is called Partitioning Procedures for Solving Mixed Variable Programming Problem back in the 1962. And Bender's decomposition has somehow been reinvented by a different community called Stochastic programming. Stochastic programming is just one small community in optimization. And then they call this method L-shaped methods for solving optimal control and stochastic programming problem in 1969. So you will see people refer to Bender's decomposition as the L-shaped method as well in the literature, right? So these two things are essentially identical. The motivation of doing Bender's decomposition is the following. There are some optimization problems where we have almost a block diagonal structure. Here, I'm showing a particular class of optimization problems where I'm just writing down the constraints of this optimization problem in a figure here, where you have some x variables, right? So recall that this whole thing, you can regard this whole thing as all the linear constraints in the model. Where if it is colored, that means the entries are non-zero. So all those entries, you can regard those blank entries as zero entries in this constraint matrix, right? And each row of this matrix corresponds to a constraint, and each column corresponds to a variable, right? So the variables here include some x variables, y omega 1, y omega 2, y omega 3, right? And as you can see here, in this type of, that's called, quote, almost a block diagonal structure, let's say if you ignore all the x variables, the problem is very easy, right? It can be decomposed by those small sub-block. Basically, you have w omega 1 times y omega 1 less than or equal to h omega 1, and so forth. So this type of structure occurs in an optimization framework called two-stage stochastic programming. Okay? So we will use the application of two-stage stochastic programming to motivate Bender's decomposition. Right? So is the structure of this problem clear? So the x here is a so-called complicating variable. So usually people call x the reason you call x complicating variables is because once you get rid of the x, the problem is very easy to solve. Right? It can be decomposed by these three separate blocks here. Right? One thing is that you can get rid of it. The other thing is that if you fix x to a particular given value, right? So let's say if you fix all the x variable to some constant values, then the rest of the problem can also be very easily solved, right? They can be decomposed by those small blocks. Okay, so then let's show an application where this type of structure will appear. So this is something called a two-stage stochastic programming. I will first give you a generic overview of what two-stage stochastic programming is. Then we will show you a very simple application. Then we can go back with this definition again. So usually it appears when a decision maker has to act in two stages. At the first stage, let's suppose you make some decisions x. Right? X can be a vector of dimension n. For now, let's think about x as all continuous variable. Right? So at the beginning, you make some decisions x. And then some uncertainty will realize. You can think about these uncertainties as some unknowns, parameters. When you make decisions x, you don't know those unknown parameters. But once you make those decisions, you know the unknown parameters. Right? We will show you an application what those unknown parameters can be in the next slide. And then depending on the resolution of these uncertain parameters, you will take the so-called stage 2 decisions called denoted by y omega. Right? Then for different realization of these uncertainty parameters, you will take different stage 2 decisions. Okay, and then we assume there are capital omega number of possible realizations of these uncertain parameters. They are denoted as scenarios in two-stage stochastic programming. Okay. Now the idea of two-stage stochastic programming is to say, because of the uncertainty, I don't have perfect information in this two-stage setting, but I want to take the best first-stage decisions x such that on average I'm doing well across different scenarios. Okay, so we'll come back to this, this definition again after we talk about a simple application. Then we will be aware what will be the first stage decision, what will be the second stage decision in a particular application. Yeah, so let's talk about the simplest application you can find as a two-stage stochastic programming problem. Right? This is called the news vendor problem. I don't know if you guys have read any newspapers. Maybe now you all read news on your phone, but in the past people do read newspapers. Then you assume there is a news vendor who go to a publisher every morning to buy X newspapers at a price as C per paper. Right? So a publisher will go to a news vendor will go to the publisher to buy newspapers, but then they don't know what will be the best number of newspapers to buy. Right? There are some trade-off in deciding how many pieces of newspapers you are going to buy. But this number is usually bounded by some limit u that represents either the news vendor only has a finite amount of money to buy the newspaper, or the publisher only has a limited number of newspapers to sell. Right? You cannot buy an infinite number of newspapers from the publisher. Then after this vendor buys all the newspapers he or she needs, then he will go to the street to sell as many newspapers as possible at the selling price Q. Right? And if they cannot sell all the newspapers, they will return to the publisher at a return price R. Right? Of course, R is strictly less than C. Right? So in other words, they got a bunch of newspapers. If they can sell all the newspapers, they are done. Right? And of course, the selling price is higher than the purchasing price. But if they buy too many newspapers, they cannot sell all of them, right? Let's say if the demand is very low, you have to return the newspapers you cannot sell to the publisher. Then maybe the publisher will recycle the unsold newspapers, right? And then in that case, you will only get a return price even lower than your purchase price. Okay. But the thing is that when they are buying the newspapers, they don't know how many papers they will be able to sell. Right? So the customer demand can be uncertain when you are buying the newspaper, right? So let's assume the customer demand is a random variable denoted by D, okay? So customer demand, you can assume it follows a given probability distribution. For the sake of the argument, we just assume maybe all the demand follow a uniform distribution, right? There can be a maximum number of newspapers you sell on a given day and a minimum number, right? And from historical data, you collect those numbers, then perhaps sometimes you even have a forecast model to forecast how many newspapers you are able to sell on the next day. Okay. But now the decision is this news vendor has to make a decision how many newspaper he's going to get before he knows the demand, right? And then in other words, these variables X are the so-called first stage decisions, right? So X is first stage decisions, and then the demand is the uncertain parameters. And then the second stage decision would be, how many you are able to sell based on the demand. Of course, you are going to sell as many you can, right? Okay. Does this application kind of make sense for now? Right? So the idea is that you want to make the decisions X such that on average, you are getting the most profit out of that, right? Or you are minimizing the cost maybe out of this problem. Okay, so just go back to this framework again. X is a first stage decision you make at the beginning, right? At stage t equals to 1, that will be the number of newspapers you get at the beginning. And then it will follow by the resolution of uncertainty. In this case, the uncertainty are the demand, right? The number of newspapers actually you can sell. And then we have the stage 2 decision that will be depending on the demand, how many you actually sell. Right? That's the stage 2 decisions. So let's formulate this as a two-stage stochastic programming problem. Right? So you have X being the first stage decisions. It's bounded by 0 to U. Right? Recall that I said U is the maximum number of newspapers you can buy from the publisher. Maybe U would be the maximum availability of newspapers at a publisher, so you cannot buy over U, right? And the second stage decisions are a bit complicated. So recall that the omega is called scenarios, right? In this case, the scenarios are different demand scenarios. For example, if the customer demand is from 10 to 100, then there are 91 different scenarios, right? That would be the either customer demand is 10 or 11 all the way to 100, then you have 91 different scenarios, and depending on the demand, your y omega variable denotes the number of newspapers you actually sell, right? Of course, you cannot sell more than the customer needs, right? So y omega is less than or equal to d omega. And the other constraint is, the y omega denotes the number of newspapers you can sell, then the z omega denotes the number of newspapers that are returned to the publisher, right? If you cannot sell all the newspapers, you will return some of them to the publisher. That's what this z omega variable represent. And of course, if you have y omega plus the omega, they cannot be greater than the availability of newspapers you buy from the publisher, right? So that's why we have these constraints, and then those numbers are greater than or equal to 0. So for the sake of the argument, we don't enforce integer constraint, right? Actually, the y omega, z omega should be an integer value, right? Let's just relax them to be continuous variables. So does the constraints make sense here? Yes?
Where is the demand established?
Yeah, so the demand is this d
omega. Where is it, how do you choose it at each iterate? I guess,
oh, yeah.
How do you know what its value is?
Yeah, so you just assume you have a model maybe. From your historical data, you kind of know what will be the range of the demands.
Okay.
For example, in the past, in some very bad days, you only able to sell 10 newspapers, and then in some very good days, you can sell 100 newspapers. So now from your historical data, you just assume the demand will be from 10 to 100.
Okay.
Right, and then they take all the integer values from 10 to 100, and that will be all your the 91 scenarios you have in this model.
Oh, so you run this for 91 scenarios?
Yeah, so you have that's a key question, right? You have an y omega variable for each scenario.
Okay.
Okay, so recall that if you have d omega, let's say, is from integer numbers from 10 to 100. Then you have, we have 91 copies of y omega variables. Right, so we have a second stage decision for each scenario in this problem, right? Okay. Yeah, so that makes this optimization problem quite large, right? Since you need to copy all your second stage decisions for each variable. For this news vendors problem, it doesn't really matter, right? You have a single variable, you just the y and the z variable per each scenario. If you have a large problem, the problem can be quite large, yes.
So for each omega, does your x keep changing?
No, right? Because you have to be committed to buy the newspaper, right? You don't have a perfect forecast. Right, that's a key question in this type of problem, right? You have to first commit to buy this number of newspapers, and then you go to sell the newspaper, right? So that's why you only have a single X, but you have multiple Y. Okay, right?
So, for example, between 10 and 100 AWs, it's going to keep changing, right?
Yeah, so the y variables are going to keep changing, right? So for example, so let's say you committed to buy 50 newspapers, right? And then you go to the next day to sell the newspaper. If the demand is 10, you cannot sell all the 50. You just go back to return 40 back to the publisher. But if if the demand is 100, you will sell all 50 of those. But kind of you are missing out the opportunity to sell another 50. Okay. You don't have, let's say, perfect information, right? You don't know, what exactly would be the demand when you are buying the newspaper.
So then what's the use of the historical, like the distribution you get from the historical data?
Yeah, so the historical data helps you to decide the optimal X, right? So the goal of this program is to give, from the historical data, you have a probability distribution. Then now you can say what will be the optimal X such that you are minimizing your expected cost, right? So if you don't have the distribution, you just make decision based on a given scenario, then probably you will do very poorly in other scenarios. Okay, that's exactly the reason you want to consider all the scenarios here. Okay. Yeah. So here, so let's interpret the objective a little bit. You have. So CX would be the cost you need to buy the newspapers, right? And then when you start to sell the newspapers, we will collect some profit, right? So we sell Y omega newspapers, then the price is at Q. And for the Z omega copies, we are going to return to the publisher. Then you get some return value of R, right? So that's this will be the let's say the maybe the money you gain in scenario omega. Okay. And for different scenario, you are going to have a different profit, right? Like what I said, when you have 50 newspapers, if the demand is actually 10 or 100, you will get different profit. Okay. But the objective is taking the average over all the scenarios, right? So let's say if you have a uniform distribution the weight you assign to each scenario would be 1 over this. You can think about this as the cardinality of the scenario set, right? If you have 91 scenarios, this number would be 91. Okay. So the idea of two-stage stochastic programming is to help you find a unique first-stage decision such that you minimize the expected cost across all the scenarios. Okay. Any questions related to this concept here? And similar things, maybe I can give you another real-life example. Maybe some of you guys are investing in stocks or bonds and so forth, right? So now when you want to invest, you don't know the return of the stocks in the future, right? But you do want to make a decision such that your expected profit is maximized, right, when you are investing in stocks. So you can also solve a two-stage stochastic programming problem if you know the probability distribution of different types of stocks, right? So that's another example of two-stage stochastic programming problem. In the first stage, you have to make a unique decision. This decision should work well across different scenarios on average in the future. Okay, so that there is a time value of information, right? Okay, so if you buy that, let's generalize this framework a little bit, right? So recall that X are the first stage decision. In the news vendor problem, those are the number of newspapers you buy from the publisher. Then Y omega are the second stage decisions for scenario omega, and tau omega is the probability of scenario omega, right? If you assume uniform distribution, tau omega would be the 1 over the number of scenarios. In other distributions, like normal distributions, you can use some discrete value to approximate the normal distributions. Then tau omega would not be equal to each other. Okay, so that's that. And then if you assume all the variables are continuous, maybe you have some constraints on the first stage decision, right? In the news vendor problem, those linear constraints are, the number of newspapers you buy is between 0 and u, right? That's a first stage constraints. And then once you decide the x, in the second stage, those omega variable also have some sort of, let's assume all the constraints are linear for now, right? Recall that in the news vendor problem, those constraints are just these constraints here for the second stage, right? So now we represent them generically using those matrices T, W, and this vector H. Okay, so and in the literature, this W is called the recourse matrix, right? So because this W matrix is associated with the second stage variables. Second stage variables are also called recourse variables, right? So that's why it's called the recourse matrix. And this T matrix in the literature is called a technology matrix, right? You don't need to remember all those jargons, but let's just assume the first and second stage are all linear constraints. Okay, any questions so far? Yeah. Then, if you look at the structure of this problem, it's exactly the same structure I told you at the beginning of this lecture, right? If you can fix the first stage variables, then the rest of the problem can be decomposed by a scenario, right? So each scenario is independent once you fix the x variables, right? So that's why I keep saying that x is so-called the complicating variables in these type of problems. Okay. Now, the motivation of Bender's decomposition is to say, if we have this type of structure, how do we leverage the structure to solve this problem faster, right? If you can decompose by scenario, you can assign, each of these second stage problem to a thread in your computer, right? If you have 1 million scenarios and then you happen to have 1 million CPU threads, then you can just solve it in parallel. Okay.
Can you explain that one more time?
Yeah. So the idea is, we want to decompose this problem by scenario, right? But it cannot be done very trivially, right? Since you have this complicating variable x, right? If there are some smart ways you can decompose this whole problem by scenario, then you can solve them in parallel if you have a multi-thread computer, right?
So are you solving for an x in each scenario in that case?
Yeah, so that's another decomposition. I haven't talked about how we are going to decompose them, but in this case, we have a way of decomposing them. And by the time we talk about, in the next lecture, perhaps we will talk about Lagrangian decomposition. Then we are doing exactly what you said. You have an x for each scenario. Here we are not copying x for each scenario. We will just fix the x and solve the rest of the problem in parallel.
Okay.
Right?
So you're fixing the x.
Yeah, so you want to fix the x in some,
okay.
Using some routine, right? Okay. Yeah, so conceptually, are we all clear on this type of problem? All right. Okay, so before we show the Bender's decomposition, we will talk about something called Bender's reformulation, right? So if you understand Bender's reformulation, you will also understand Bender's decomposition. So let's go through this very slowly. Maybe you have already forgotten some of the concepts from linear programming, but we will revisit that, right? So if you don't feel lonely if you have forgotten something. Maybe it's very common you forgot something from linear programming. Just remind me if you have forgot something, then we will talk about that again. Yeah, so there is a very simple way of reformulating the problem. Right, so recall that in the previous formulation, we have minimizing C transpose X. Then we have, you can think about you have an optimization problem for each scenario, omega, right? So now we just define a function called eta of X, right? So eta is a function, you can think about it as a function of X, which basically shows the minimization problem in the second stage for a given X, right? So this is nothing but we are rewriting the two-stage stochastic programming problem as the minimization problem over X, and we are representing the second stage problem using this function eta of X, which is essentially minimizing the second stage problem if you are given an X variable. Okay, so the way to interpret this eta function is you can think about this as a recourse function, right? Once you are given an X, right? Let's say if you have a fixed X, this recourse function is giving you the minimum of the second stage cost for each scenario. Okay, so again, you want to minimize X to minimize the expected cost in the second stage. But now we are writing the second stage problem as a function of X. Once you are given different X, you solve this problem that is parametric on X, right? So you're in the second stage, you are minimizing Y omega for each scenario omega. Okay, so this is nothing but a rewrite of the original problem. Okay, yeah. So here, now if you look at this recourse problem, right? So you are given an X, then you want to minimize the second stage, right? It's, in the news vendor problem, it's saying if you fix the number of newspaper you already purchased, then for each scenario you are optimizing for the number of newspaper you should sell, right? That's what essentially this eta omega of X is doing, right? Well, fixing the number of newspapers you get, then we are going to determine the optimal number of newspapers we sell and return to the publisher. That's what this problem is doing, okay? And now, if you think about this recourse function, it is a linear programming problem with respect to the Y variable, right? All the constraints are linear, Y is a continuous variable, right? And for linear programming problem, I assume all the people are familiar with how to take the dual of a linear programming problem, right? So if you have this minimization problem by strong duality of linear programming problem, you have it's equal to this maximization problem over the dual variable, right? So the dual variable is p omega here. Okay, so far so good. Yeah. Then in this problem, we assume the dual problem is always feasible. Okay, sometimes the primal problem can be infeasible, but we assume the dual problem is always feasible. This is always true when the primal is bounded. I'm not going to show a proof. Maybe you can just believe me if all your variables are bounded in the primal problem, which is the case, right? For most of the problem, you assume all the primal variables are bounded, then your dual is always going to be feasible. Okay, so I'm not going to the detail of that. You can try to show that as a take-home question. So if the dual is feasible, then there are two cases that can occur, right? So remember that when optimization is feasible, there are two cases that can occur. The first case is that this problem is unbounded, right? Well, a feasible problem can be unbounded, right? When you maximize something, it goes to plus infinity. That's what means optimization problem is unbounded. And when we say an optimization problem is unbounded, right? Yeah, that means okay. That's this part. We'll talk about that before. Maybe people have forgot about that. That means there exists an extreme ray that will take the objective to infinity, right? You can go along this extreme ray, and then the product of the extreme ray with the objective is strictly greater than 0, right? So we will revisit what an extreme ray is next. Yeah, so besides the case that the dual is unbounded, another case is that the dual is feasible and bounded, right? So if a problem is feasible, it can be either unbounded or bounded, right? And then when the dual is bounded, we know that the optimal solution can always be obtained at an extreme point. Right? That's a result we get from linear programming. Okay. Yeah. In other words, when you are solving the dual problem and the dual problem is feasible, then you either get an extreme ray or you get an extreme point, right? When the problem is bounded, you hit an extreme point, which is optimal. When the problem is unbounded, there is an extreme ray that can take your objective to infinity. Right? So let's review what is an extreme point and an extreme ray here. Right? So recall that an extreme point is equivalent to something called a basic feasible solution. Right? Hopefully people still remember that. Essentially, to get an extreme point, you just take n linearly independent constraints and make them active, right? Remember what is a basis in a simplex method, right? That's just n linearly independent constraints that give you an extreme point. An extreme ray, from a geometric perspective, this is an unbounded polyhedral set, right? So an extreme ray in this unbounded polyhedral set are essentially these two extreme directions, right? So if an optimization problem, a linear programming problem is unbounded, we know that there must exist an extreme ray. If you go along the direction of the extreme ray, the objective will go to plus infinity, right? That's what we mean by unbounded. And to find an extreme ray, you just need to take the cone of the polyhedral, and then you set n-1 independent constraints to hold, right? Then you will get an extreme ray. So those are the definitions. If you have forgot about that, just revisit the linear programming notes. Okay, so let's go back here, right? To summarize, when we are solving the dual problem, there are two cases that occur. Either it is unbounded, where you hit an extreme ray, or if the problem is bounded, you must hit an extreme point. Okay, is that clear here?
So, Professor,
yeah.
So are you using the dual problem to print out the feasible region of the
Yeah, so that's a good point. So since you have the primal and dual here, which problem you are going to solve, right? So in practice, you just formulate the problem as a primal problem, and you can get the dual. Since in the simplex method, the primal and dual have a very nice correspondence, right? The solver will, even if you are solving the primal, the solver will return a dual value to you as well. So you don't really need to worry about translate the problem into a dual problem. Okay. Yeah. Any other questions here? Yeah.
So, I have a question.
Yeah.
What was the motivation for taking the dual? Like, if
Oh.
it was infinity, it could also have been like gone to minus infinity. So why was like the dual taken? It was shown that it could go to plus infinity.
Oh yeah. So that's a primal dual correspondence, right? If the dual is unbounded, then the primal is infeasible.
Okay.
Right, so that's a primal dual correspondence. Yeah. But we assume the dual is always feasible. Then the only case the primal is infeasible is because there exists an extreme ray in the dual make the dual unbounded. Okay, so that's a good question. Why we are taking the dual? You will see that in a second. Why we are taking the dual? Okay. Yeah. So another thing to refresh your memory is that do people still remember the Minkowski-Well theorem? And anyone would like to talk about what is Minkowski-Well theorem? It's related to extreme rays and extreme points. Anyone? No? Okay. Yeah. So probably you want to refresh your memory again. If you so if you study linear programming, I would say the three most important things are the following, right? First is Minkowski theorem. Second is you can take dual in the LP. The third thing is that the optimality condition of the linear programming methods, right? So the Minkowski-Well theorem is saying that so any polyhedral set is the convex hull of its extreme points and the conic hull of its extreme rays. So now when I write it down, does it at least sound a little bit familiar? Okay, yeah. So in other words, besides describing linear programming problem as some linear inequality constraint, you can describe any polyhedral set by its extreme points and extreme rays, right? Okay, so that's what we talked about before in the linear programming class. And from the definitions of extreme points and extreme rays, we can at least have the following conclusion, which is there are finite number of and extreme rays, right? And this is clear because when you are getting an extreme points, you are making a subset of the constraint to be active, right? There are only finite ways of choosing those active constraints. So there are finite number of extreme points. And for the extreme rays, you are also picking a subset of those inequalities and let them hold as equality, right? And there are finite number of combinations of those. Okay. So that's that. Now, how do we derive the Bender's reformulation? Okay. So here's the key observation why we are taking the dual. Okay. The key observation is the following: if you take the dual of this recourse function, you recognize that this polyhedral set, the feasible region of the dual, doesn't depend on the x, right? Okay. So even if you change the x, this feasible region will still have the same extreme points and extreme rays, right? All those, all those parameters are independent of your first stage variable. Okay. Yeah. So therefore, the optimality condition and the feasibility condition of this optimization problem are independent of x. Okay, so let's argue why it is the case, right? So first of all, if you want to enforce the following condition, you want x to be a feasible solution, right? Remember I said if you pick some first stage solutions, maybe your second stage problem is infeasible, right? So when the second stage problem is infeasible, that means the dual is unbounded, right? So remember this primal dual correspondence. If the dual is a lower bound of the primal, if the dual is plus infinity, then the primal must be plus infinity, right? So, but if I'm minimizing, plus infinity just means infeasible, right? Okay. So let's say if you want to pick the x that are primal feasible, then you must have the following, where all the product of the extreme rays with respect to the objective has to be less than or equal to 0, right? Remember when the dual is unbounded, that means there exists an extreme ray that will lead your solution to plus infinity, right? So in other words, if you want x to be feasible, then all those products must be less than or equal to 0. Okay, so you must have those, all the product of extreme rays with respect to these coefficients in the second stage to be less than or equal to 0. If x satisfies this condition, then we know that the dual problem is bounded. Is that clear? Maybe. Yeah. So again, the trick is the following, right? The feasible region of the dual is independent of x. Okay. So that's is saying that the extreme rays of this feasible region doesn't depend on x, and then you can characterize a finite number of extreme rays. Okay. And in order for x to be feasible, you cannot let p go along the extreme ray direction and still have a positive product with these objective coefficients, right? So in that case, all the extreme rays product with the objective coefficients has to be less than or equal to 0. Okay. Maybe someone should ask a question here. Or let's talk about the second case first. Perhaps that will help you digest this extreme ray as well. So, So let's assume for the sake of the argument, the dual is bounded, right? Meaning that it is primal feasible. Okay. Then for any x, where do we get the optimal solution, right? So we know that the optimal solution is always obtained at an extreme point if the optimization problem is feasible and bounded, right? So essentially, a very naive way of solving linear programming problem is just I enumerate all the extreme points in this problem and pick the best extreme points, right? Essentially, simplex method is more or less doing that, right? It's a smart way of enumerating the extreme points. Let's just do a reformulation. We have the set of pi omega denoting the set of extreme points of the polyhedral set, right? So if this optimization problem is feasible and bounded, I'm essentially picking the best extreme points over the set of all the extreme points, right? So you're kind of picking the max over the set of extreme points that give you the highest value on this objective. Okay, so eta will be equal to this, right? If you are picking the best extreme points. And the trick here is, again, right, the extreme points doesn't depend on x, right? So since your polyhedral set doesn't depend on x, all the extreme points doesn't depend on x. You're just picking the best extreme points out of all the extreme points. Okay, so that's a trick of taking the dual, basically. If you are solving the primal problem, x would be, in the primal feasible region, right? Then it will, all the extreme points of the primal problem does depend on x, right? If you take the dual, the x will be moved to the objective, and the feasible region of the dual doesn't depend on x. Okay. Yeah. So if it's not clear, you can go back, try to revisit your linear programming notes and come back again. Okay. So with that, we can have a Bender's reformulation. Right. So essentially, what we have is the following. Right. If the problem is optimal, we are taking the max over a bunch of linear functions, right? So in other words, you can reformulate this max over the linear functions as omega is greater than or equal to all those functions, right? All those linear functions corresponding to the extreme points. And the other thing is that the extreme rays must have negative product with the objective. So you have those constraints as well, which make sure that your first stage decisions are feasible for the second stage, right? So in other words, these type of cuts are called optimality cuts, and the second type of cuts are so-called feasibility cuts, right? Recall that the optimality cuts correspond to all the extreme points in the dual. The feasibility cuts correspond to all the extreme rays in the dual, right? So the optimality cuts guarantee that if the problem is feasible, you get the optimal solution over all the extreme points. The feasibility cuts guarantee that you cannot go to infinity on those extreme ray direction. Yes.
I'm sorry. How is that optimality cut? Like, what's like the explanation for it being written that way?
Oh yeah.
Greater
So you
than
are
yeah.
yeah. So you are in the last slide we wrote something like this, right? The eta x is equal to the maximization over so let's write it as p omega I h omega less than t. So that's the way we are writing the the optimality over all the extreme points, right? But since this max function it is not linear programming problem, right? You cannot have a max in a linear programming problem. So you need to translate the max into linear inequalities, right? So this is equivalent to saying that the omega is greater than equal to each piece of this linear function, right? So if you want to have some geometric intuition, that would be this function is taking the max over a bunch of linear functions, right? You can think about the linear function as let's say so let's say we have 3 linear functions, and you are taking the max over these 3 linear functions. That will be using green here. So the max of these 3 linear function is this green function here, right? That's the max of those linear functions. And then if you write omega to be greater than or equal to each of the pieces here, right? That essentially you are talking about the epigraph of this the 3 linear functions, right? That will be let's say this constraint will be denoting this red region here, right? So that this red region is eta greater than or equal to all those linear constraints. Right, so that's what this linear inequality is representing, right? It's this red region above the max of all the linear functions. Okay, so this is not equivalent to the max function, right? Remember, the max function is the green function here, right? It's just representing this line here, right? But if you are doing the eta greater than or equal to all the linear pieces, it's this whole red region here. But why this is a exact formulation? The reason is because we are minimizing over eta here, right? So if you are minimizing over eta, the optimal solution will always be on this green line here, not above the green line, right? So that's why this is a valid reformulation.
Is the idea that the dual problem lower bound is the Prackle problem? I guess.
Dual.
I guess that's why like
No.
the extreme points on that. Maybe not. I don't know.
Not really. It's more like you are taking the max over a bunch of linear functions. The max over linear function is convex, right? Then if you are minimizing a convex function, that's fine, right? On the other hand, if you have a maximization problem, this no longer works, right? If you have a maximization problem here, you cannot, do the max over eta. It will, the optimal solution will be unbounded in this case, right? That wouldn't work. So the reason is that this is a max over, linear function, and the objective is minimizing over eta. That's why it works. So be very careful here when you reformulate the max function, right? Okay. Any other questions with the reformulation here? All right. So what's the issues with this reformulation, right? Now you kind of get a linear programming problem with only the x variable. There are no, this optimization problem is essentially minimizing over x and all the eta omega here, right? You get rid of all the y omega variables, which is nice. You are solving a problem with smaller number of variables. But on the other hand, you are introducing a combinatorial number of constraints, right? The number of extreme points and extreme rays can be extremely large in an optimization problem, right? So the Bender's reformulation is even more expensive to solve than the original problem, right? Because basically you are take some heavy lifting by enumerating all the extreme points and the extreme rays and add it to this reformulation problem. So this is definitely not practical. So what Bender's decomposition does is an iterative method to find those active cuts, right? So imagine there can be, even for a very small problem, there can be millions or billions of optimality cuts and feasibility cuts. But in the optimal solution, only a small subset of optimality cuts and feasibility cuts are active, right? So imagine that you only need the cuts that correspond to the optimal dual, right? You don't need the cuts that are not optimal or done. So in that case, Bender's decomposition is just an iterative method of generating the optimality cuts and the active optimality cuts and feasibility cut for you. Okay. So how does Bender's decomposition work, right? So you can draw an analogy to the generalized Benders we talked about last time, right? We first solve the so-called Bender's master problem. In the master problem, let's assume at iteration k, you only have a subset of feasibility cut and optimality cut, right? Perhaps you can assume at iteration 0, no cuts are added, right? You just solve this first stage problem, and then you give a trivial lower bound on the second stage cost eta, right? You can think about in the first iteration, k equals to 1, you just write eta omega greater than or equal to L. L is a trivial lower bound for eta, okay? And then as you go around the Bender's decomposition methods, you keep generating the feasibility cuts and optimality cuts when it is needed. Okay. So the way it works is that let's first solve the Bender's master problem with only a small number of optimality cuts and feasibility cuts, right? Then you get the optimal solution to the Bender's master problem at iteration k. You can denote it as x superscript k, right? So again, the Bender's master problem only has those x variable, right? You just solve this linear programming problem with only the x variables. Then after you solve the master problem and fix x equal to xk, remember what we told you is that x are the complicating variables, right? Once you fix those x variables at xk, all the rest of the problem are decomposable by scenario, right? So if you fix x to xk, you can solve the so-called Bender's subproblem by scenario, right? If you have, let's say, 1 million scenarios, you can, just solve 1 million small problem instead of solving the big problem, right? Essentially, decomposition is that you have a master problem, only have the x variables, which is also a quite small problem since you are not including any second stage decisions. And then once you fix x, you can solve each scenario in parallel, and each of those are also very small problems, right? That's how it works. Yeah, so if you fix x equals to xk, you can solve the minimization problem in the second stage. Of course, it's equivalent to the dual problem. If you are implementing Bender's decomposition, you can just implement it as a primal problem, and then you can get the dual from Pyomo. Okay. Yeah. And then once you solve the subproblem, as I said, there are two cases that can occur, right? Either the second stage problem is unbounded, where you will generate an extreme ray. If it's bounded and feasible, you will generate an extreme points of the dual, right? So it's kind of like you are generating the extreme rays and the extreme points based on the solution of the subproblem, right? You can kind of interpret it as, you are finding the extreme points that are violating your, the constraints in the Bender's reformulation. Okay, so let's go back this again, right? Recall that in the Bender's reformulation, we have a very large number of extreme points and extreme rays, right? You are essentially having all the extreme points and extreme rays here. But now you want to find out, what are the useful optimality cuts and feasibility cuts. The way you find it is you only keep a small subset of those here, and then you add them when they are violated, right? So it's kind of like cutting plane type of methods. Once you find they are violated by solving the linear programming subproblem, then you add them back, right? So each time you solve the linear programming subproblem, you will hit an extreme point or an extreme ray, and then you add them back to the master problem. And the master problem then will give you a new solution. You can keep iterating between the master problem and the subproblems. Okay. Here's some detail of how to really implement it to generate a feasibility cut, right? So usually when you use the solver to solve the Bender subproblem, if the problem is infeasible, you couldn't get an extreme ray out of it. The solver will just tell you, this problem is infeasible. How do you actually get an extreme ray out of the Bender subproblem? Okay, so now we will talk about, in practice, how do you get an extreme ray from the subproblem. The way to do it is that if you know the problem is infeasible, you can do the trick. We have been using this trick multiple times, right? Add some slack variables to make the problem feasible. Okay, so here you can think about for each of these equations, we are adding some slack variables called S omega plus and S omega minus, right? And they are all greater than or equal to 0, right? So if you add a slack to each of these equality constraints, they must be able to make this problem feasible, right? And in the objective, we are going to penalize the slack variable, right? So in other words, you want to make the slack variable as small as possible such that the primal problem becomes feasible, okay? So, and then if you take the dual of this problem, you will find, you will get a bounded dual problem, right? So this, if you take the dual, you can try to take the dual to see if I take the dual correctly. Then you will find out the dual variable will be bounded if you add, add the slack variables here. So the dual will be bounded between -1 and 1, okay? And then we will have this is the polyhedral cone of the original problem, right? So remember, when you want to generate the cone of the polyhedral set, you just set the right-hand side to 0, change it to P transpose W less than or equal to 0. So with that, you will see that the variables you get from the dual, of course, it will be bounded since it's bounded between -1 and 1, and it also satisfies this constraint. It will give you an extreme rate of the original problem by doing this. Okay. Yeah, so just to summarize, how does Bender's decomposition work, right? You solve the Bender's master problem, which has a subset of those optimality and feasibility cuts. It will give you a lower bound of the original problem. Okay. So why I say it provides a lower bound of the original problem? Any thoughts? Remember, we are minimizing, right? And the Bender's reformulation is an exact reformulation of the original problem, right? But now I'm keeping a subset of optimality cuts and feasibility cuts, right? So why it is a lower bound here?
Because the second stage constraints will be more tight.
Yeah, so can you argue in a more rigorous way why you have a subset of cuts, it is a lower bound? What do you say? Not really. Any other thoughts here? No? Okay, so it is a lower bound because recall that when we have a Bender's reformulation, right? The Bender's reformulation is equivalent to the original problem, right? We showed that already. Right? This is a reformulation of the original problem. But what I said is that the Bender's master problem only have a subset of the cuts in the Bender's reformulation, right? So essentially, you are in the Bender's master problem, you are relaxing some of the constraints, right? If you are relaxing some of the constraints and you are minimizing, it will be a lower bound of the original problem. Okay. And then we fix the solution from the Bender's master problem. Then we solve the Bender's subproblem. And the subproblem will give you an upper bound. Why that is an upper bound here? Yeah, exactly right. Because it is feasible to the original problem. Right? Any feasible solution to the original problem is called an upper bound, right? Okay. And the optimal solution is the optimal one. A relaxation of the problem is a lower bound, right? Okay. And then you will converge when the upper bound and lower bound is less than or equal to epsilon. Of course, you will converge in a finite number of iterations because there are a finite number of extreme points and extreme rays. Okay. So I just want to make sure the why it is a lower bound and upper bound is clear. Otherwise, we cannot go to some of the other optimization problem, right? So any questions related to why it is a lower bound and why it is an upper bound here? Okay. Now, so this is something not relevant to the algorithm, but it is a geometric interpretation of Bender's reformulation, right? I thought about whether I should talk about this or not, because if I talk about the interpretation, the idea is to make you understand this problem better. But if it makes you more confused, you can just forget what I will talk about in the next few slides. Okay. So this is a geometric interpretation of Bender's reformulation, right? So think about the original problem as a problem where, the original two-stage stochastic programming problem has the x variables, the y omega variables, and so forth, right? It has both the x and the y variables. But in the Bender's reformulation, it only has the x variables, right? So essentially, the geometric interpretation of Bender's reformulation is to project a problem in high dimension to a low dimension problem, right? In other words, project a problem with both x and y variable to an object with only the x variables. Okay, so maybe people are more confused. So let's talk about, does anyone know what a projection of a set means in mathematics? Okay. So let's talk about this. This is a very basic concept in mathematics. Okay, what does projection of a set mean, right? If you have a set in high dimension, in dimension real numbers m plus n, right? Think about x has n dimension, y has m dimension. Okay, so you want to project this set onto the x space, right? What will that give you? Okay. So the projection of a set to a low-dimensional space is essentially saying that you take all those points in high dimension, and then if the x coordinates is in the set, then it will be in the projection. Okay, so that might be too abstract. Let's look at this 2D example here. Okay, so we have a trapezoid shape, right? Let's say the 2D set is this set here, right? What is the projection of this set to the x space? Okay, so here I draw the projection in the red line. Okay, so basically what I need for the projection is if I pick an arbitrary point here, right? Let's say I pick this point here, then I will look at this set saying, is there any point whose x-axis equal to this value here? There is no point in this set whose x value is equal to this particular value here, right? But if I pick any points, maybe let's write this as a black line here. Let's say we have a point A here. So no point in this set has a coordinate of A, right? If I pick any point on this red line, let's say if I pick B here, then I know there is at least one point in this set whose coordinate is B, right? And if I pick this extreme point C here, at least one point in this set has a coordinate of C, right? So that's why I say that the projection of this high dimensional object to the x-axis is this red line here, right? So if you want to define it formally, okay, remember this definition here. So the projection of the set to the x space is that all the x coordinates such that there exists at least one y such that xy is in the high dimensional set, right? So there exists at least one point whose coordinate is x in the high dimension. This is a definition of projection in mathematics. Okay, so Bender's decomposition is essentially doing projection, right? So the y variables in Bender's decomposition are those second stage variables, and the x variables are the first stage variables, right? So you can think about the feasible region of the master problem as a projection of the full space problem to the x space. Okay. So how do you project a polyhedral from high dimension to low dimension? Okay, so there is also something called a projection theorem, which says if you have a polyhedral in high dimension that has variables u and x, and you want to project this polyhedral set onto the x space, right? So essentially we are rewriting the definition of projection, right? So projection to the x space is that for all the x, there exists a u such that this point ux is in the high dimensional polyhedral. Okay, so how do you project it? There is something called projection theorem. Basically, you need to find some vectors that are the extreme rays of this set here, right? So you can think about those v as like your Lagrangian multiplier, right? You want to kind of cancel out all the constraints related to the U variables, right? So you have V transpose A equals to 0, then you are going to cancel out all those U variables and be left with the X variables, right? Right. And you don't need all the ways that are in this polyhedral. You only need the extreme rays, right? So remember, in Bender's decomposition, we have something related to the extreme points and extreme rays, right? So in order to do the projection, you only need those extreme points and extreme rays to project the two-stage stochastic programming problem onto the Bender's reformulation or the Bender's master problem. That's a geometric intuition of Bender's decomposition, right? If someone not in optimization asks you how do you explain Bender's decomposition to a non-expert, this will be a way to explain it to them, right? Essentially, you are doing projection. Okay, so now I will switch gears on a slightly different problem. Up until now, all the problem we talk about only have continuous variables, right? What if we have a problem with mixed integer first stage variables, right? And in the second stage, we still only have continuous variable. Does Bender's decomposition still work under this circumstance? Any thoughts here? Right. Again, the problem setting is a little bit different, right? Now we introduce some binary variables in the first stage, and the second stage are still continuous variables. Think about the derivation, right? How did we derive all the Bender's cuts and so forth? Does this setting still work? For yeah, exactly, right. So if you fix the binary variables, the second stage problem is still a linear programming problem, right? So the way we derive the Bender's cuts only depends on linear programming duality, right? So since the second stage problem is still continuous, the same derivation still holds, right? So you can, the only change is that the master problem is an MILP, the sub-problem is an LP, okay? Actually, if you remember what we did in the previous lecture in generalized Bender's decomposition, right? The master problem are binary variables in generalized Bender's decomposition. And the second, you can think about the second stage problem in generalized Bender's decomposition is a convex nonlinear programming problem, right? But in that case, we were using the Lagrangian duality instead of linear programming duality, right? So in generalized Bender's decomposition, in general, you cannot guarantee finite convergence because you don't have finite number of extreme points and extreme rays, right? The beauty of linear programming problem is this, finite characterization of the feasible region. Okay, yeah. So it will still work. The only change is that the master problem will become a mixed integer linear programming problem. Okay, so how do we implement Bender's decomposition, right? If you have mixed integer variables, the thing is that you can still, iterate between the MILP and the LP subproblem, but it's not very efficient because you are redoing the branch and bound in every iteration. Okay, a more efficient implementation is a single tree Bender's implementation. It's just the same thing as in the single tree outer approximation methods. We are only doing, in other words, in the Quesada-Grossman algorithm, we are doing branch and bound only once, and then we are adding those cutting plane on the fly, right? So the same intuition hold is that you can have a single tree implementation where you start doing branch and bound, and you add Bender's cut when you find an integer solution at the node of the master problem, right? So to implement that is not very trivial. To implement that, we will need some callback functions in the solver. We will have a lecture on callback functions in the future. So if you want to read more, there is a very nice blog written by the optimizer Paul Rubin. You can take a look at his blog. Okay, so let me talk about one more extension of Bender's decomposition. So I said that if we have mixed integer first stage variables and then the second stage variables are continuous, we are fine, right? We can still do the LP duality. But if we have second stage mixed integer variables, then we cannot use the same Bender's cut anymore, right? In the second stage have integers, you cannot do the strong duality resulting linear programming, right? So then the question is, how do we solve this type of problem, right? But for here, we are restricting the first stage variables to pure binary variable. Okay, so that's a restriction we have to derive something called the integer L-shaped methods. But if we have mixed integer variable in the first stage, the problem is too complicated. That's not within the scope of this class. Okay. So how do we solve this problem with mixed integer second stage variables in Bender's? But the first stage variables are all binary here. Okay. So there are two types of cutting planes or Bender's cuts we can still derive. The first type of cuts are so-called LP relaxation-based cuts, right? Because in the second stage, you have some binary variables. You cannot take the dual anymore. What you can do is we will relax the binary variable to be a continuous variable between 0 and 1, and then we derive a cuts from that. Okay, yeah. Now the question is, why are those cuts valid for the original problem, right? So you are relaxing the second stage binary variables, and then you derive feasibility and optimality cuts, right? So why are those cuts valid for the original problem? Any quick answer here? Yeah, exactly, right. So you are kind of relaxing some of the constraints here, right? So if the original constraints hold, then the LP relaxation constraint have to hold, of course, right? Right. So that's why those cuts are valid. Yeah, but the thing is that with only the LP relaxation-based cuts, you won't converge to the original problem, right? Because the original problem have those binary constraints, but now you are relaxing them. Okay, so that won't guarantee convergence. If you want to get convergence, we need to add something called integer cuts to cut off the solution. Okay, don't look at this formula for now, right? The high-level idea is that if you get the first stage variables, and now you just solve the second stage problem with the integrality constraint to optimality, right? Right. So it's like kind of evaluating the first stage binary variable you have in the second stage with the integrality constraints, right? And you will get an integer feasible solution. If you solve this problem, that will give you a feasible solution to the original problem, right? Since it's you have the integer constraints here as well. Okay. And the cut you can add is that telling the master problem, don't give me the same integer solution again, right? So it's like an integer type of cut, right? So you can validate that, this form of cut is valid when you have integer second stage problem. Essentially, the set are, if you remember the formula of the integer cut, this is very similar, right? So the set B denotes all the binary variable equals to 1, set N denotes all the binary variable equal to 0, and then you have this form of cutting planes to cut off this integer solution. The L is a trivial lower bound of this objective, right? So you can try to evaluate this type of cutting planes. So if you hit the same integer feasible solution, you know that this term will go to 0 if you, not go to 0. So this term will be equals to BR when you are hitting the same integer feasible solution, right? Since the number of variables equal to 1 is B, and number of variable equal to 0 is in N, right? So if you hit the same solution, this is BR, and then the second term is BR minus 1. So essentially, you will get this eta R value again when you are hitting the same solution. Okay, so here's a very easy proof of validity. You can try to prove it yourself to see if it is valid. And just very quickly, this is not required in this class, is there's something called nested Bender's decomposition. The idea is that how do you apply Bender's decomposition in a recursive fashion? Okay, so if you have a problem with this type of tree structure, right? So let's say if you hide if you treat this whole thing as a master problem, then the rest of the problem can be decomposed by those z variables, right? But then you realize that this master problem can be decomposed again by x and y variables. So you will decompose it again, right? So the nested Bender's is like a way of recursively applying Bender's decomposition. Okay, I will just give you a reference. If you are curious about that, you can read it into more details. Essentially, in nested Bender's decomposition, you will have a so-called forward simulation and a backward recursion. The forward simulation is to give you a feasible solution of the original problem, and the backward recursion is to add Bender's cut in a recursive manner, and then you go forward and backward. At the end of the day, you will converge. Okay, so this happens when you have, instead of a two-stage stochastic programming problem, and you have a multi-stage. Let's say you have a three-stage stochastic programming problem. It will follow this pattern, and the algorithm to go is called nested Bender's decomposition. Okay, so here's all the references of this lecture. You can take a look. Especially this is a recent review paper on Bender's decomposition that talks about all the state-of-the-art techniques.